Yeah, hello, good day, everyone. It's a pleasure to welcome you all to today's exciting lecture on quantum teleportation. Yes, we have dived deeper into the realm of quantum mechanics. We are about to explore one of the most fascinating phenomena, that is quantum teleportation. Unlike the teleportation we see in science fiction, this process involves transmitting the quantum state of a particle from one location to another using the magical concept of entanglement, which I'm sure you have heard before. So it's going to be interesting with the principles of superposition and uncertainty, which will also play a key role in understanding this concept. We are excited to have our facilitator with us today in the person of Richie to take us through this exciting lecture, which is just going to be part one, and other parts will come later. Thank you so much, Richie, for joining us.
Yes, today we're talking about quantum teleportation. This is largely based on the Quantum in Picture book that Stefano and Bob has written. And last week, or maybe last lecture, you had a chance to listen to what Stefano has to say about these pictures that we're using to try to kind of better explain or elucidate how we understand quantum theory or quantum computation. So I'm going to first do a recap and feel free to ask questions because we have a lot of time. As a quick recap, the main language we use to describe quantum computation in this book is using these boxes and wires. We've seen lots of examples in the last lecture about how these boxes and wires can be used to model things in real life, such as modeling electrical components being connected together, or like recipes on cooking things. But in this talk, I'm gonna go straight into describing how these boxes can be used to describe quantum theory. So let's say you have a box here, and the way to read these boxes or these diagrams is from bottom upwards. So kind of if there's some sort of notion of time, then time flows from bottom to the top. So here you have a box or diagram with n input wires underneath here, and you have m output wires at the top. So this would represent a quantum process with n qubit systems going in and m qubit systems coming out. So you can represent that as a linear map with dimensions 2 to the n to 2 to the m. And similarly, if you had a box with no input wires and then with only output wires, so let's say here you have also n wires, this will represent an n qubit quantum state. So this would be a vector in a vector space with dimensions c2 to the n. Does that make sense so far?
Yes.
Yes. Yeah, feel free to ask any questions if it doesn't make sense, because we have a lot of time. Let's say you had two boxes, U1 and U2. And they have dimensions C2 to the N1, C2 to the N2, and the output dimension is C2 to the N, or M1, C2 to the M2. Then the combined dimension would be taking if you write these boxes side by side, then that represents the tensor product. So this will be written as, you can think of it as one big box. And you can think of it as a linear map from C2 to N1 to N2. to c to the 2 to the m1 plus m2. And you can also compose these if the dimensions match up. So if you're familiar with how the quantum circuit model, then you can think of quantum circuit. This is a very generalized version of quantum circuit model. Okay, cool. I'm not sure whether this was covered last time, but I'm gonna go through them again, which is transposes, daggers, and conjugates. So given a linear map again, you can take the vertical flip. So I'm gonna add. What I'm gonna do here is I'm gonna draw this rectangular box as a trapezium instead of regular rectangle. So you can see how I'm rotating or reflecting the box. So if I reflected it this way, you can think of that as I call this a vertical reflection, but it's actually a reflection on the horizontal axis. So hope that's not too confusing. Then this corresponds to taking the dagger of a linear map. And if you, I mean, that's just taking the transpose of the matrix and then taking element-wise complex conjugate of each entry in the matrix. So if this was M, then M dagger would be, well, and now we just reverse these entries. So I'm taking the transpose. On the other hand, if I just took the complex conjugate, then I'll get something more like this. So I'm actually now doing a horizontal reflection along the vertical axis. And now the types are still the same because I'm just reflecting. So the input output types are still the same. Like this, these are the types. And as you can see, the conjugate is just and if I do these operations one after the other, I'll arrive at something that's in fact, I hope I get this right. Yes. I'll actually end up getting the transpose of the matrix. Sorry, this is, yeah. So you compare to the original matrix, that's just, transposing the entries of the matrix. You're just swapping B and C, and there's no more complex conjugates. This is just obviously these are just very simple linear algebraic operations, but we can represent these graphically. And the way we draw these boxes is just showing how it's just implicitly encoding the fact that if you do a transpose, then a conjugation, you're in fact doing the dagger of a linear map. This will end up useful later. Just going to wipe out some of this stuff. Okay. So suppose you have a transpose of a matrix. Then you can also think of it as by just deforming the diagram, because as it was mentioned in the last talk by Stefano, deforming the diagram doesn't actually change the actual final value of the diagram, which is changing the way it's being presented. That would be very good. So you can see how this diagram is written the same way as the other diagram, but with the actual original matrix rotated. This is also a transpose of a matrix, but now you can see the original matrix like explicitly written out here. And furthermore, if you look at these bent wires, you can also think of them as boxes themselves. You can think of this as a very special kind of box that is drawn using wires. And that's the next point. When you draw a box like this with no input wires and two output wires coming out, and the box is drawn using just wires, we're actually representing something that is known as the Bell state. So in linear algebraic terms, it's written out like this. In bracket notation, it's written out. Like this. On the other hand, if you take the dagger of it, so again, a vertical reflection, then that is just the dagger of this vector, or in this case, also the transpose. So I now have this kind of flat row vector, and in bracket notation, it's written out like this. Does that make sense?
Yes, please.
That's good. Okay, so let me talk about unitaries and isometries now. So that we've learned about the vertical reflection, which is a dagger of a linear map. If you have, well, okay, let me draw it from here. If I have a linear map, and it happens to be the case that if I compose it with its dagger, they end up canceling out and I get the identity, then M is known to be an isometry. And the reason for that is, suppose you were comparing the inner product between two vectors, A and B, two quantum states. If I've rotated both A and B, or like transformed A and B by the same operation M, the same isometry, then I'll end up getting something like and you get the same thing. So this tells you that That's why it's called isometry, really. It preserves distances. And furthermore, if you have the same equation, but kind of flipped around. So if I had the original matrix written like this, and then I flip it around and I actually pre-compose it with its dagger, that equals identity as well, then you would say M is unitary. Okay, so this will be useful later when we talk about quantum teleportation. Non-determinism. Okay, so I mentioned a special kind of box where there's no input wires. So let's say you have this quantum state psi, and you want to test how similar it is to another quantum state. Let me think of a symbol, phi. Then one way to do it is to join up these two boxes. And in bracket notation, it's very similar, really. It's just the same expression but written sideways. So this is equivalent to taking the inner product between two quantum states. And it happens to be that when you measure a quantum state, when you perform a quantum measurement, and it doesn't coincide on exactly the same basis, then oh, I got a comment. I think you should put a dagger on A2. Let me see. Yes. I think you're referring to this bit, right?
Yes, please.
Yes, it's so actually it's just slightly confusing notation. So like if you have a cat and you take the dagger of it, that's just you just write it as a bra like this. So this is implicitly daggering the A as well. But yeah, good observation. It's just like a confusing notation. Yeah. It's a bit like if I had, you can think of this as a diagram, this is a diagram, but drawn sideways. But yeah. Yes, exactly. Yes. So, but this is a good question. Okay. So sometimes when you do I think all I want to say on this slide is sometimes when you do measurements, you get different outcomes. You can't control the outcome of a state that isn't, fully deterministic. Is what I would say. So like let's go back to for example, let's go back to this cup example where this is unnormalized, by the way. So I might add a root 2 just to keep it more proper. When you measure this normalized quantum state now, you're gonna get 0, 0 or 1, 1 with equal probability. And that's not something you can control. Yeah, that's all I want to say for now. Okay, so I think we now know enough parts, enough like background to start talking about quantum teleportation. So how does quantum teleportation work? Okay, I'm going to draw this with a dotted line just so it doesn't crowd up the screen too much. Yes. So let's say there were two people, Alice and Bob, and Alice had a quantum state. that they wish to transfer to Bob, but there's no like quantum channel to do so. There's no like way of like just copying a quantum state, which we know is impossible by the no cloning theorem. You can't just copy a quantum state and send to Bob. So how would we do it, right? Well, fortunately, the quantum teleportation protocol tells us that if Alice and Bob share the maximally entangled state, known as the Bell state, that I've drawn here, then it's possible with some work high above here for Alice to transport this quantum state to Bob. Well, how would you do this? Actually, does anyone want to give a suggestion on how this might look like? Using these pictures. So you want to end up in a scenario where Bob ends up with this
Sir,
quantum state. Yes, hello?
please, could you go over the question again?
Yes, so if Alice has a quantum state here on the left that they wish to transfer to Bob like so in the right-hand side, and they happen to already have this cup, this Bell state in the beginning, what could Alice add here to turn this into the right-hand side diagram? I'm happy to take any answer. So it doesn't matter whether you're like not completely sure about the answer. What is missing in that compared to the right-hand side diagram? I guess I can wait for like a minute before I review the answer.
Hello?
Hello.
I think it's going to be the same thing, the same.
So what do you mean by the same? So what would I draw in the question mark?
The same triangle facing downwards.
Yes, the same thing facing downward, exactly. So that's the answer. Nice. So like this. Right? Okay. Thank you. Thank you. Yes. So yeah, from what we learned so far, if you just completed the rest of the diagram like this, if you had this box joining the quantum state that Alice wishes to teleport and the Bell state that Alice and Bob share, then we know from just rewriting their diagram, because we know that this is true, that you'll end up getting this, that Bob would eventually share Alice's quantum state. So so far this is all very abstract. So it doesn't really mean much because it's just a picture. But let's look at it again. So let's make this a 1-qubit example. Let's say the state that Alice wishes to teleport is of this form. this diagram, if I just look at this whole thing, the quantum state tensor product with the cup side by side, then in terms of bracket notation, it's going to look something like this. So now I'm just multiplying it out. And if I look at this subpart of the diagram, if I view it as a single linear map, then I will have something like this. Does this make sense so far? Or if I've made a mistake, feel free to point it out. I'm just multiplying everything out.
Hello. Hello.
Hello.
Yeah. With the second bracket that we have ket 0, bra 0. Will that be a unitary?
Ket 0, bra 0. Where's that? Oh,
No,
here.
not.
Yes, this would be a
Yes.
unit, right? This because this is the identity operation. So
Okay.
it takes in 0 and outputs 0, and it takes in 1 and outputs 1. So if I took this diagram, that's a good question. So if I took this diagram, 1 second, and I joins it with its reflection, that is in fact equal to identity.
All right.
Matches the definition. Yeah, that's a
Thank
good
you.
question. Yeah. Yes. Yeah, I appreciate it's a bit silly now because we're just drawing wires, but later you'll come across spiders and other things that allows you to define more complex linear maps. Then it will start become more interesting. Oops, sorry. Okay, so I realize I've written a lot here and it's not very clear. But if I join up, sorry, hello?
Hello.
Yes. Hello.
Yes. I think the tensor product,
Yes.
does it commute when you take the tensor product of two state? Does it commute?
Is the
Looking at
tensor
the
product? Sorry, hello.
does do tensor product commute?
Okay, that's a good question. So in general, tensor products do not commute, just because yeah, you can find very simple examples that don't commute. So if you had, I mean, normal multiplication commutes. So this is true. But if I had two matrices, even like 2 by 2 matrices, that is not in general equal to B tensor A. So that's a very interesting property of the tensor product. It doesn't have to be. It normally isn't commutative.
All right. Thank you very much.
Mm-hmm. You're welcome. So if you join up this with this, you see how there's 1, 1, 1 here and 1, 1, 1 here, and 0, 0 here, and 0, 0 here. These brackets are going to join, and well, the basically inner product of anything with itself is equal to 1, right? So you're going to end up getting the original quantum state. But yeah, this is just to show what the equivalent calculation is in normal bracket notation. It's very, long-winded. It's not very enlightening. But on the other hand, on the left-hand side, you can see just by drawing this picture, you have some concept of how quantum teleportation looks like or is implemented. But there's actually a problem with why it's drawn earlier, is that basically this picture, this thing, which I'm going to call cap effect or a Bell effect. Actually, I think it's in the book, it calls it like a test. I'm going to call it a cap test or a Bell effect. These things aren't always implementable deterministically. So the slide I had earlier about non-determinism, this is what's going on. So what actually happens is when we try to apply we could get 4 possible outcomes. So the first outcome is you actually do get what we wanted to implement, which is the usual Bell effect, which is good. But you might also get this. So these are the 4 possible outcomes. I haven't really said what A, B, and C are. I think this is something that will be discussed in later lectures. But all you need to take away here is when you try to apply a Bell effect, you apply a Bell measurement, and you will get one of these 4 outcomes. And outcome 1 is good. The other 3 are bad. And you need to do some sort of fix. You need to fix this. Does this make sense so far?
Please, sir.
Yeah. Okay.
Hello.
Hello. Yes.
Okay, what are those ABC?
Yes. So like I said earlier, like these boxes are just linear maps, but I actually haven't told you what the linear maps are. But that's a good question. So I might in fact write them out.
Okay.
Yeah. Thank you for your question. So this is the first one. As you can see, this is just the the transpose of the, well, yeah, this is just the dagger of the Bell state, right? One of the other outcomes you might get is that instead of having the plus here, you will have the minus. So instead of plus adding the two bars together, you actually take the difference. Here's another one you might get. This is the final one. And this is kind of just a bit of both. So in terms of matrices, you're going to get, this is the first one, and that's good. Might draw it a bit tighter. So this is a row vector again. This is a row vector. This one looks a bit like this. And this one's going to look a bit like this. Don't want to get the sign wrong. Which minus should it be on? Should be on this one. Does that make a bit of sense? Does that clear it up? Okay, hope that's okay. Thank you for your question.
Yeah, it is okay, sir. Thank you.
Yeah, I forgot to connect it to linear maps. I think once you connect to linear maps, the picture is a bit clearer. So I need to make a new page now. Not sure how to do that. I will copy this slide. No, I can insert blank page. Fantastic. Fantastic. So let's visit this again. So in the case where, well, let's start from the beginning. Alice still has a quantum state that they wish to give to Bob. And Alice and Bob share this Bell state, this cup. Now Alice tries to teleport the state to Bob by applying this Bell test, or this cup test or Bell effect. But most of the time ends up having this error. Right? So now what ends up happening is Bob will get this. Oh, sorry. Hope I rotated it correctly. Oops, I have not. So instead of getting the original quantum state, Bob will get this. Can everyone see that just from drawing? Just from rotating this box over here.
Yes.
Yes, that's good. So in fact, without extra information, Bob can't learn anything really about Alice's original state. So that's something you can prove using quantum theory. But now if Bob knows which error, if Alice applies this test and works out which test has actually occurred and communicates with Bob which one it was, then Bob can apply a corresponding correction. Look at this. Yeah, so it turns out that because this error box is in fact an isometry, this is actually equal to, they just cancel out. So Bob actually finally arrives at the corrected quantum state that Alice had, no errors. Cool. So this is quite nice, I think. So as a bonus, we can do something called entanglement swapping. So how does entanglement swapping work? Let's say there's Alice, Bob, and Charlie, 3 people. And now Alice and Bob share this Bell state, so share an entangled state. And Bob and Charlie also have some entanglements. But in fact, what they want to happen is that what can we add here so that Alice and Charlie end up with an entangled state instead?
I think you can complete it by doing an upside down curve.
Yeah, so exactly the same thing again. So even though they're different protocols and the calculation looks different, the idea is actually very similar. And yeah, the idea is exactly the same. Bob can apply this Bell test and get an error. And as long as Bob communicates that error to Charlie or Alice, then they can make the correction. And now they end up with a longer entanglement between themselves without Bob. Now I won't write the calculation out here, like using linear algebra, because it's very, very long. And so I actually find this example of entanglement swapping very beautiful because once you understand the concept of how quantum teleportation works using these diagrams, then coming up with the solution for entanglement swapping, even the formal one with these isometries and corrections, isn't too hard. And on the other hand, if you only had pen and paper and you had to write out all these bracket notations, you can get lost in the notation and everything, and you don't really see why it works. You can see the calculations, but and see that it does in fact work. But I feel like this gives you a better picture. So yeah, this is everything I want to say so far. Well, yeah, this is all I want to say today. Talk about entanglement swapping and quantum teleportation. So I'm happy to just take any questions. So yeah, thank you for having me, and thank you for listening.
Thank you so much, Richie, for the wonderful presentation. We would like to take a few questions from the participants if they have any. Please, if you have a question, you can unmute yourself and ask the question, please. You can also decide to use the chat room to ask your question if you have any.
Hello.
All right, Abdullah.
Hello?
Please, I don't know. The entanglement part, I don't really get it. I don't know. Is it the Bell state measurement? Is it is it what changes the maybe is it the main cause of the connection, the interaction between the two different entangled states? Is it the Bell state measurement?
Sorry, can you repeat your question? Is it to do with entanglement swapping?
Like what I mean is that you have two different states. Let's say you have one box having two qubits that are entangled, another box having and another box B having two states that are entangled, and then you want to measure the Bell state, right?
Yeah.
So
Okay.
is it that measurement that connects the two states, or is it what exactly connects them? I don't really get.
Yes. Okay, thank you for your question. So let's draw again. So more generally, you can have kind of two arbitrary quantum states. And what happens in practice is you measure here. Oh, sorry, the writing is not very clear. You measure these two wires, and these two wires represent quantum systems. So on a quantum computer, these would be two qubits, or like two sets of qubits. And when you measure the quantum system, those qubits will be gone. So you can no longer apply new operations onto the qubit. So this is a destructive measurement. But after that, you will have, if you look at the whole picture, you'll still have a two qubit quantum state. And this two qubit quantum state, in the case of entanglement swapping, corresponds to the Bell state, like I have in this picture up here. But the key here is that this measurement here has to be an entangling measurement. It has to be a Bell measurement. It can't just be two separate single qubit measurements. That wouldn't entangle the quantum state. So there's a special kind of measurement that would actually entangle the two states. Does that help you answer the question?
Yeah, I think that's good.
Yeah, it's like it's a special operation that can entangle the two states. But you still need to make a correction for it to be corresponding to a quantum state that we care about, which is here, the Bell state.
Yeah, thank you.
No problem. So I think I have another question here. Is it okay to think of a state as some sort of information? If yes, then teleportation about the transfer of information from one region. Yes, with the aid of some linear transformation. Okay, thank you for your question. Yeah, this is the way to think about it. So a quantum state, normal classical data, classical state would encode binary information like ones and zeros. And here you have a quantum state. So yeah, this in fact encodes some quantum information. I'm not going to talk about how like quantum information exactly relates to classical information, but yeah, this is in fact what's happening. Like, quantum teleportation sounds like some sort of sci-fi movie phenomenon, but this is just a practical way of how we can transport some quantum information from Alice to Bob. So yeah, that is a good way to think about it. And the linear transformation is just the kind of calculations we need to like describe the physical phenomena that is occurring.
Okay. All right. Thank you so much. If there are not any more questions, we would like to thank you for the wonderful presentation. And we look forward to the more future sessions we are going to have with you. Thank you so much. And to our participants, thank you so much. We would like to remind you that tomorrow we have a talk. So we look forward to seeing all of you online as well. Thank you. Okay, all right. We would also like to remind you that all lecture videos are on your virtual e-learning platform, and all talks are on the YouTube channel. So kindly do check. Aside the lecture videos, we also have materials for you as well. So the pre-materials, the lecture, their slides, they are all available to you on your e-learning platform. Thank you all so much.
Thank you for having me.
All right.